of regular expressions.
So you know this talk is going to be about the real computer science because it's on paper from the 60s. I'm a firm believer that as of 1970, all real computer science stopped happening.
Is that why you have the Unix here?
Definitely. Strong believer. Yeah, I do all of my coding on Lisp machines, or at least I would if there were any. So I'm going to talk about derivatives of regular expressions for no reason other than I was on Reddit last month at the meetup, and Reddit was like, you should read this blog post about derivatives of regular expressions, and I was like, cool, I'll give a talk on that next month. And then I read the paper eventually. So, what is a regular expression? That's fun. So I'm going to go with, because I'm reading an academic paper, I'm going to go with the academic definition of a regular expression, which is exactly the same as what you think a regular expression is, except that it's unrelated in every way. So a regular expression is a set of strings. That's what it is. So for example, this is a regular expression. Right, that's a regular expression. This is another regular expression. Right, that's a regular expression, right? We don't normally think of it this way, because normally we, if we were doing software development with regular expressions, you sort of talk about regular expression as a language for describing patterns that can be matched in strings. But I mean, ultimately, what you're saying is you're describing a set of strings. You're saying either a string does match, i.e. is in this set, or is not, right? And so usually your sets are going to be bigger than this, and so you want to describe them using a more powerful notation than this. So you're just talking about how to generate how to characterize a potentially very large set, a potentially infinite set of strings using a compact notation. That's what regular expressions are all about. So the problem is that as soon as you have a non-trivial regular expression, usually it becomes non-trivial to then actually do anything interesting with it in using the classical methods that we have. So the normal way to, so like the normal operations for academic regular expressions are, you can take an expression, so you get what? So the base grammar that they usually use is like you can have a letter, which can be any letter from your chosen alphabet. Alphabets are usually finite. I don't even know if infinite alphabets are allowed out, but they're finite for any purpose that we care about. And then you can have any regular expression that you can use a clean star to say there are zero, this is one occurrence, this is zero or more occurrences of whatever expression you have. You can, I can write so well, you can do this, and you can do this. So you can concatenate and you can do disjunction, and that's like everything that you can normally do. Yeah, in fact I may have even added a thing. Like the number of operations you need to be closed is extremely small. But nobody writes regular expressions using only these operations, because that would be dumb. Because if we wanted, because it turns out the minimal set of operations you need to describe all sets is not what's interesting to us, because the whole reason to even have regular expressions is to have a compact expression language for potentially very complicated sets. We're not interested in minimalism. If we were, we would just write them all, and then we'd be done. Right? We want an expressive language. So that's the thing we want. But a thing we also want is for it to run fast, because we are not doing something very hard, and so it should be fast, and also it should not take all of our space. That would all be nice. So the way that undergraduate students get taught in university courses to deal with regular expressions is there's like a transformation from the regular expressions to NFA, where you have some automata that you can follow multiple paths at once, and then you do the construction to get DFA out of that, and your DFA is an exponential blow up of your NFA, and then you do minimization again, right? So the problem with this process is that it's retarded, and so no one does it. No one in the whole world uses this process.
I did for my project.
Yeah. No one in the whole world who is not a student in the undergraduate level of science, right? Because of course, yes, you will use it if you are being, but because it's not only has the potential for, but quite often will have, if not exponential, at least extremely large space blow up when you're generating the initial DFA, and then you have to do a big crunch down. So there's all kinds of algorithms that sometimes they talk about and sometimes they don't, about like running the NFA directly or like all these weird things. So what's very popular out in the world in implementations, like if you look at Ruby and JavaScript and Python and Perl, they do what's called backtracking, which is where you just try and run the regular expression pretty directly. You just see like, does this character match? Does it match what I think is happening? And if not, then like we'll pop back to the other part. So if you want to do a disjunction, you'll like try and match this. And if it doesn't work, then we'll just roll the whole tape back and try and match this. Like you get rid of the whole automata thing and you just actually try all the branches of, you basically use the NFA style and you just try every branch in order. And it's ridiculous because then you have exponential runtimes, which is better than exponential space on most computers, but still bad. And then they're like, but on most regular expressions, most of the time, it's not actually exponential, it's good enough, unless you accidentally use negative look ahead or any of the other features that you actually wanted because you're trying to use an expressive language. So then you had projects from Google like RE2, where they basically banned a lot of operations to try and make it fast. And then they do a sort of DFA construction and stuff. But basically the problem is that we want a minimal DFA. There exists a minimal DFA, but our classical way of constructing the DFA first constructs an NFA and then an NFA to DFA conversion that results in a giant stupid DFA, and then we try and minimize it. The obvious thing to do, if it were possible, which it is to make a smaller DFA in the first place. And we don't want NFAs, those are not good. You can only run them using backtracking or by converting them to DFAs, so why would we want them? Because both of those are bad.
Or a non-deterministic computer, obviously.
Right, yeah.
If we could have one of those, that'd be great.
That's right. We could definitely do that.
Quantum computers.
Yeah. So obviously our
No.
obvious solution to all of our regular expression needs is quantum computers. But since those won't happen in my lifetime, we're going to do this. So this paper from the 60s is better than everything you've ever seen about regular expressions, in my opinion. I'm probably wrong about that, because maybe you've seen really cool things about regular expressions. But it's better than everything I've ever seen about regular expressions, which is like, all that matters because I'm giving the talk. Yeah, basically you just construct, well, it's a little, it's not really about constructing the DFA at first, but they define this thing for the purpose of constructing the DFA. So what is the derivative of a regular expression? So the paper uses this notation, so I'm going to use it. The paper is in this really weird PDF format where what I'm seeing is clearly a scan of a piece of paper, but when I highlight, the text is there, but it's a little bit wrong. So it's like they OCR'd in behind the picture. It's like the worst piece of garbage ever. But it was free. Speaking of that, everybody should go and use Sci-Hub. Sci-Hub is the best thing ever. Seriously. So
with the dash?
Yeah. So basically, you're like, Sci-Hub isn't the best thing ever because most of the time you don't want to read academic papers because they're unreadable pieces of garbage. But if you can't find any good summary of the topic you're on and you have to read an academic paper, then good luck.
So it's reading the paywall?
But yeah, you're Googling around and you end up on dl.acm.org and they're like, please give us money. And you're like, cool. And you copy the URL and you paste it into this website and they give you a PDF.
Oh, wow.
And I don't think the PDF is shitty because of them. I think it's shitty because of ACM. They just gave you the PDF for free. Yay.
One of the top Google suggestions for Sci-Hub is Sci-Hub or Russia.
Yeah. So, yeah. Anyway, that's my plug for Sci-Hub. Everyone should use Sci-Hub. Or, find something better than academic papers to read in your spare time. Yay. Okay, so the derivative with respect to some string of a regular expression R is, I'm just going to use it's T where ST is in R. Because, look, see, sets, because everything is a set. This was really confusing. If you go in and you forget that regular expressions are just sets, then this makes no sense at all. But otherwise, it's fine because you're just saying you find all of the sequences that start with S in your set. Everything that doesn't start with S, you just throw out. You don't care about those. Everything that does start with S, you keep, and then you chop the S off, and the result is your new regular expression. That's it. That's what the definition of the derivative is. There are rules, obviously, like normal derivatives, for how you can do that in a rules-based way, so you don't have to think about this too hard. But it is this is what it is. This is when they make. It was kind of weird to me because they're defining the derivative. And then they're like, yeah, so then this rule is the rule. And then they're like, now here's the proof that this rule works. And I'm like, why do you need a proof? This is your definition. And I was like, oh, no, right, this is the definition. And they have to prove that this rule does satisfy this. So that's a real thing.
Everything else is just convenient.
Also fun, I don't know, academia is weird. They have a couple of the proofs where they're like, this proof is really long, so we put it in the appendix. You don't really care anyway. I was like, wait, I don't. If I don't care, why did you do it? But if I do, I don't know. Someone cares who did it, I don't know.
Very easy.
And then they had one proof, it's not even in an appendix, it just said, this proof follows easily from the proof in this other paper, so it's fine.
I've done that before in assignments.
No problem. It's totally, you can see obviously how it would work, it's fine. We just took his theorem, we inverted it, it'll totally work. Yeah, so that was fun. I'm not going to do any proofs though. Unless I have lots of time and people are really interested, but I doubt either of those. Okay, what am I talking about? Derivatives of regular expressions. This is it. I should do an example, that's what I was going to do. So if I have at and abs and car, and I do the derivative of this with respect to the string A, then I get T and BS. That's what I get. I don't get car because it didn't start with A, and I chop away the stuff. Right? The fun thing about this is that, so there's an algorithm that I will talk about eventually for using this to generate the DFA, obviously. And there must be such a thing, but that's why I spent all that time talking about it in the first place. So this means that if you can define rules for finding the derivative of an operation that satisfies this definition, then you can get a, if not minimal, almost minimal DFA for that operation in a regular expression. So crazy operations that you never would have thought, any binary operation on regular expressions. But there's fun facts. For example, they have this operation, which I would normally write like this, right? The complement of R, which is just the regular expression that matches everything this regular expression doesn't match. This is a binary operation because it takes two regular expressions and ignores the second one and returns the complement of the first one. So when they say any binary, they mean anything that takes two regular expressions and produces a new regular expression. It doesn't have to use both inputs. So unitary operations are totally fine. They're just lazy. They don't want to talk about it because the proof is the same in both cases. And you can do that. You can do the inversion because so they have the rules. Let me write the rules for the common operations because they're fun. The derivative of A with respect to A is empty string, which they write as lambda, and some people write as, I'll just do this. It's like empty string, right? And then the derivative with respect to A of B is the empty set, right? Sometimes written as that. And this is for any B, I mean, blah, 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 right? It's paper. This is for any B that's not A. If B is A, then that's obviously A applies. You follow the rules in order. So they have proofs for all of these. So I'm not going to do them. So clean star, right? That's a good one that we might want. So So some people, it's interesting, some of the talks that I've watched about this concept seem to think that these rules that I'm going to show you are exhaustive, and they'll be like, yes, the derivatives approach defines these operations, but like the whole point of this paper is that they're like, no, you can define new operations, it's fine. Basically any Boolean logic operation you can imagine, we could add, it would be fine. As long as you can come up with a way to write this rule, which you probably can. So this is right, so it's basically just recursive all the way down, right? You just, they write the parentheses the other way apparently, I don't think it matters. So you just take the derivative of one copy and then like the rest of it. Yeah. Star, and then they have, so this one is more complicated. This is the most complicated one, is concatenation. So, PQ. I'm going to translate their notation into something more sane a little bit. I know this notation is maybe not what you consider sane to begin with, but bear with me. It's better than what I'm reading.
In those equations, does A represent a character or a regular expression?
A represents a string. Actually, I believe these particular rules are for characters, but they go on to then extend them to strings, like basically trivially.
It looks
Yeah,
like
this
it's a character.
this is definitely for character, but they extend it to string trivially by basically they have three rules. No, they have one rule, which is basically that if you take the derivative with respect to a string, then you just apply these rules successively for each of those characters in a nesting fashion. I can write that rule at the
You
end.
just can't have a bar or a star inside of it, like the A or the string.
No, because it's just a string. It's not a regular expression. It's definitely a string. You're always deriving with respect to a regular with respect to a string. It's the derivative of the regular expression with respect to this string, which in this case is a single character, but then the extension is a single rule, which I can get to. So delta of P. So this is the complicated part because I skipped delta because it mostly doesn't matter, but it is in this rule. So this is for concatenation. So what this says is that the derivative of the concatenation of PQ is the disjunction of the derivative of P concatenated with Q and delta P concatenated with the derivative of Q. So delta P is just a simple function that, I'll just write it. It's, I'll write the simple version of it. It's up here. So this is just a helper function that they define. So delta of R is its empty string if R is nullable, which is to say if empty string is a member of R. So remember R is a set. And it is the empty set otherwise. That's it. So it's basically just a way of checking whether or not a regular expression is nullable. So what this says is if P can match empty string, then empty string goes here. And if we concatenate empty string with the derivative of Q, well, that's just going to be the derivative of Q. So we're good. So this will all result in either the derivative of Q or nothing. Because the other possibilities, you get empty set concatenated with any set is the empty set, and so the whole thing is empty set. So so this side is straightforward. We take, because we're looking for prefixes, remember that we're stripping prefixes. So with PQ, either P is the prefix, in which case we take the derivative of the prefix, and then the suffix is there, or the P contains empty string, in which case maybe the prefix is in Q, because P could be empty string, in which case we take the derivative of Q. That's what this is. It's a complicated way of writing that. Does that make sense? Yeah, okay. I just made it up, so I'm glad it makes sense.
Now, just if it's the empty set case in that function there, that means that the right side failed. Is that what that means?
For this, so here we're just saying
No, I'm looking at the function up there, the,
Yeah.
it's the empty set case.
Yeah, it's empty set case if there is no empty string in on.
And so that means it would be a failure case, that right side then would not.
For this?
Yeah.
Well, it won't be a failure case, it'll just be empty. So,
Yeah, the empty set is not something that's found in normal regular expression languages. It's in the theory, but it's not in like Perl or anything like that.
right, there's no way to write a regular expression that matches nothing. Unless you write a regular expression that matches everything and you negate it, if you have the ability to negate regular expressions.
Which you normally don't.
Which you normally don't, but we totally do. So you can write it in this case. There is an implementation, in fact, that I should talk about. Well, there's several, but it's called RedGrep. And the RedGrep talk is actually pretty accessible. So if you're interested in looking that talk up,
Okay.
it's pretty good. It's by the guy who wrote RedGrep. There's a couple implementations of RedGrep, but he's the original author of the original implementation. It's not necessarily like Great Shakes implementation or anything, but it's fun. He implements some of these concepts in a pretty straightforward way to do various different things, including generating LLVM bytecode for regular expressions, which is kind of fun thing that he does. He also has a dot output so that you can just generate the DFA and view the graph with dot, which is fun. So that's the thing. But it's big, massive C++ code that I can guarantee you uses the auto keyword. So I'm like, but it exists, and that's fun.
So
okay.
your Delta has basically like a maybe or an option.
Yeah, exactly. This is totally a math implementation of an if statement, right? They're just trying to say this whole thing is, just DAQ in the case that P contains empty and nothing otherwise. That's what this whole construction is about. There's just not a cleaner way to write that in math that I'm aware of. The first time I saw it, I didn't really get it because I forgot that when you take the Cartesian product of an empty set with any other set, you get the empty set again, and I was like, what is happening? But yeah, that.
You want it to look like the product rule for derivatives?
Yeah.
So,
They're trying to mimic things, yeah, for sure. So their last rule, the rules aren't like super important, except for if you're like writing an implementation, in which case they're obviously. So this is the part where it becomes binary, right? I mean, it could be non-binary, but they wrote a rule for binary functions, so that's just what you do. So this is fun. It's just the obvious thing.
I was going to say, it's not the obvious thing.
I can write. Obviously, it can be done. Look. Success. Yeah, it's the obvious thing. Right? So, for inversion then, right, if you want this, the rule for inversion is that you take the derivative of P and you invert the derivative. And that's the derivative of the inversion of P. And you ignore Q because it doesn't matter, because it's unitary. Right?
restrictions on F for this to be true?
Probably.
It's not true for concatenation, right, in the previous line.
Right, that's why they have that written separately. I'm gonna, do you want me to, okay. Oh,
Yeah.
they definitely have some words. So I think the way that they talk about this is that this is, F is a logical connective. So this works for XOR, it works for AND. Those are the two example implementations of F that they have. XOR, AND, and NOT are all example implementations that they have.
As set functions.
Right, as set functions. Yeah. So like AND is intersect, and XOR is XOR, and when you treat OR as union, right?
So that's what you get point-wise on the sets instead of concatenations and nonsense.
Yeah.
Okay.
Also, I believe that, no, yeah, so like you'll see, for example, that OR is normally part of this construction. There's no specific rule for OR here. This is the rule for OR.
Or is union.
Right, yeah. So this is the rule for union, intersection, XOR, and inversion, like complement, which you can do. You can't normally take a complement of a set, but we can because we have finite alphabets. So it's reasonable to think about the set of strings that aren't in this set because the set of all possible strings is known. So it's just the difference between the set of all possible strings and the set that you have. So that difference is definitely definable. You can think about that. So it says Boolean function. We shall denote any Boolean function. So we have complement and intersection and sum or union. Of course, all laws of Boolean algebra apply. Yeah. Product star and F are called regular operators. Yeah. Just being crazy people. But yeah. So that's specifically what they're talking about here is normal Boolean algebra operations as applied to sets. Which is basically anything you could want that isn't one of these. Basically. Certainly more things than you normally have. And this is for expressive power. They're still doing economy of notation here because they're proving things. Like we have character classes and ranges and things in our normal, but you can easily translate those into one of these, right? Like a character class is just a disjunction. This is fun. He talks about this in the red grep talk. He actually implements it this way in red grep. If you have a negated character class like A, B, C, then this is actually not of A, B, C, and dot, which is fun.
Intersection.
Yeah, intersection. So it's all of the strings that do not contain ABC, but then restricted to the strings that are one character long. That's what, right? So you don't even need this because it's just a special case of this. Things like that. So that's kind of the idea here, is that you're getting by importing basically the entire Boolean algebra, you're getting enough power. You don't have to do any weird hacks to get any of the operations you might want, and then everything else is syntax in the regular expression language that you can translate into one of these operations in a fairly straightforward way. In a pre-processing step that takes basically no time. Okay. And then we wanted to know about things that are more than one character long. Those I'm gonna 1 to AI of R, right? So we're gonna do a string, and it's just DAI of DAI minus 1 of stuff DA1 of R. That's what it is.
Oh, yes.
Yeah. Which is again, I can't close it. There's an infinite number of opens.
Please dots to close it.
Or just use a pi.
Close.
Or you can just say, or just put a big pie there and just have that.
Yeah. Well, that's I normally I hate dot, but like that's what they wrote, and this operation doesn't really necessarily have an alternative. This isn't. Yeah, I don't know. Anyway, I didn't think about it hard enough to invent that, but you're probably right. Oh yeah, and then they have this fun thing where they just write this identity, just in case anyone might be confused, where the derivative of empty string, which like now you start to see why they don't write that, and they write something like this instead. The derivative of empty string with respect to R is R, obviously, because you chop nothing off the front and you get everything back. Okay, so that's our rules. These rules are not necessarily the only possible rules, and they're, whatever, but they are complete on the set of things the paper is interested in, and they all satisfy this. So this is the interesting thing, but this gets your head. Then they talk about all kinds of stuff. They talk about generating regular expressions based on DFAs, all kinds of stuff that no one cares about. No one wants to do any of that. There's another paper later by Knuth talking about using this kind of stuff to do matching without generating the DFA. So basically what you do for that is you just repeatedly, you match the character in like a backtracking style fashion, and then you take the derivative of the regular expression, and then you match that again, and you just keep doing that until you either end up with empty string or empty set. And empty string means match, and empty set means no match. So that's basically the same. So we're basically that's a direct step from the construction we're going to do, where basically that's what we're going to do to construct the DFA, and then you can just not construct the DFA if you want. But constructing the DFA is faster because you don't have to repeatedly take the derivative if you're matching more than once. You're going to reuse this thing, right? So, and then they prove a whole bunch of things in here, which is fun because this is the property that I was going to talk about. There are what they call the characteristic derivatives of R, which is to say that there is a set of derivatives of any regular expression which fully characterize the original regular expression. And this set is always finite. They prove that in various ways. This set is, you can find this set with a really easy algorithm. Basically what you do, because the thing is that the set of strings that your language is over is probably infinite, right? So the derivative with respect to like the number of derivatives possible is actually potentially infinite, or at least very large, depending on, like if you have a finite alphabet and finite size strings, then maybe you actually have finite, but like it's still very big. So you don't want to take the, with A out to forever, and you never consider a B yet. That's ridiculous. So what you do is you order the strings in your regular expression that matches everything, that is your whole language, by length, from shortest to longest. And then you do the derivative with respect to all the single character strings, all the two character strings, etc., until you end up with having gone through an entire length without finding a new derivative, a derivative that you haven't already found. And if you do like all the 4 character strings, and every derivative with respect to every 4 character string of the regular expression is the same as something you found already in the past, then you're done. You have every possible regular expression. Now, regular expression equality is a complicated concept because while set equality is a straightforward concept, actually comparing 2 regular expressions to see if they are equal when they might have been produced through various rules that you applied is somewhat complicated. So they define some rules here to say that you don't need, basically they say there's some identities, basically, that you do. And it doesn't actually matter which ones you pick. You have to pick ones that are, they have a set that they then prove completeness on, which you can find, if not too far, if I want to find it, is here somewhere. Come on. But basically you just take these identities and then you normalize using them, and then if those are equal, you consider them equal, and you consider them similar, and if not, then you don't, and that's still enough to make it so that all your properties hold, and you'll just probably have to check a few more than you would have had to, and then as you add more identities, there are fewer and fewer things that you have to do, but your normalization becomes more expensive, and then it's just a balancing act on that. The identities are pretty, like their base set is pretty simple, if I can find it, but maybe I can't. Because this paper is dense, because it is a paper. Yeah, that's your X. And this is the thing where they're like, this is so fun. The theorem is a modification of a theorem of Arden, 8, who has shown that this other equation has this solution. Therefore, the proof parallels his proof and will not be repeated. So fun. Go read his paper and then figure out what we do. It's fine. Yeah. I don't know. It's somewhere in there. I can't find their subset. It's like 3 identities that they have. Fine. Really, it doesn't really matter because any identities you pick will potentially work. It'll just maybe take you like, you might end up not actually reducing your search space a lot, so you should pick good ones. That's basically the upshot of that. So, okay, so the algorithm for constructing a DFA. That's the sort of the meat here. Oh yes, so they have this theorem that states that two states in the DFA are indistinguishable. That is, they would be reduced by a simplification pass. That is, if you start at either one, the strings you can match from that point through the rest of the DFA are equivalent. If and only if the derivatives of the regular expressions at that point are similar. That's basically the hinge on which this whole thing goes. And then they prove that. So let's go through an example instead of talking about the algorithm in an abstract sense, because that's more fun. So this is the simplest example they give, which is fun. So it's 0 or 1, star 1, right? So any number of zeros or ones, and it ends in a 1, right? So you always start. We're going to do our derivatives in order from shortest thing in the language to longest thing in the language. This language is a set of all binary strings. The shortest binary string is the empty string. So the derivative with respect to the empty string of R is R, right? Always, which is great. So we introduce a new state because we found a new derivative. So each new derivative we find corresponds to a state in our DFA. So we introduce a new state in our DFA. Here it is. This is going to be our starting state because it's the thing from which you can match the whole regular expression. And it is a non-accepting state because this regular expression does not contain empty string, right? As you can see, because it must end in a 1. So it does not contain empty string, so we say it is not an accepting state, so that's fine. And there we go. That's it. So they actually have this fun thing where they're like, yes, it's not an accepting state because, delta from before of R is empty. It's like, yeah, sure, because it's not. Yeah, so then it doesn't matter which one we do next. We're going to do delta sub 0 because that's the order they go in. But I mean, we could probably do a delta sub 1 or a derivative sub 1. That would be also fine. Right, so let's do the derivative of this with respect to 1. Let's try and do it from our rules. So first we have this clean star. All right, so we have to go inside.
Top of this index.
Okay, you're right. Top is concatenation. I'm getting ahead of myself. So we do this thing, which is a big mess, right? So we're going to say the derivative of this chunk, right? So derivative with respect to 0 of 0 or 1 star, followed by 1, or delta p, which is this, and we can say right now that that in fact is epsilon. So epsilon, and then derivative of this, which we can say is empty, right? Because it's 1. So we'll just do that in line, because 1 is not 0, which is what we're respect to, so it's empty. So this whole thing is empty, so we don't actually care about that at all. So we're just going to go over here, right? And then we get inside our star. So we say that the derivative of this first thing, so the derivative with respect to 0 of 0 or 1, and then concatenated with 0 or 1 star, and then we
And 1. And then 1.
Extra one.
The one from before.
Oh yes, that one. Good. Yep, so this is all fine now. So now we're going to come down to this one. So we just push our derivative onto the inside of either side, and derivative with respect to 0 is empty. Right. So this is empty or empty side, right? Followed by this stuff, 0 or 1, star 1, and empty or nothing is empty, and empty on the front of a regular expression is you can get rid of. So the derivative is 0 or 1 star 1, which is r again, right? Is that what they said? It is, yay! Which is just r. So we have not found a new one. So we do not create a new state because we haven't found a new regular expression. But we do create a transition for finding 0 to the state that matches that. So on 0, we transition from the R state to the R state because we start there. Yeah, right? That makes sense to everybody? And then with respect to 1, we do this again. I might as well do it just because it's fun to be wrong a lot. Okay, and then our other side here, okay, 1, no. It says is empty in here, it is, so empty. And then the derivative of q is again 1, but with respect to 1, that's empty. So this is empty on this side, right? So we can simplify that to just empty for now. And then we do this side. So we say that this is derivatives of 1, of 0, or 1, followed by 0 or 1, star 1, and then we'll keep our 4 empty, because that's relevant still. And then inside here again, we take this is going to be, again, nothing or empty on the inside there, which is empty, which is on the prefix again, so it goes away again. So the whole thing is 0 or 1, star 1 or empty, which is R or empty. So we're just adding empty to R. This is different than R, so it's a new state. So we create a second state, right? And then our transition on 1 is to that state. And this is an accepting state because it contains empty. And make sure that's what they did. Yep, that is what they did. Okay, so, but we're not done yet necessarily because we haven't, in this set, like in the set of strings of length 1, we found one new regular expression. So we're not done. We haven't found all the characteristic regular expressions for this, or derivatives for this. So we take the derivative with respect to 0, 0, which I will just, or 1, 0, sorry, we can ignore. We can ignore all the ones that start with 0 because 0 did not get us anywhere. So we can skip that if we want. Like, we could do it if we want, but it would be pointless. So we know to skip it. So we do the derivative of 1, 0 of r, which I will not do because it is just r. So we say, okay, if we get here and we get a 0 after the 1, then we go to the r state, which we have already. Okay, and then we'll continue on. Derivative of 1, 1 of r is, humorously, is r or epsilon again. So that's fine. Don't need to introduce a new state. We do that one. And in this whole pass of 2 lengths, we did not find any new regular expressions. We created no new states, so we're done. That's it. That's the DFA. We did it. Hooray. So DFAs are always run in linear time on your input string because you just check the loops 1, 1, 1, 1, 1, 1, 1. So once you've built a DFA, your match comparison time for any regular expression is always linear on your input string, which is fun. So as long as you can produce them efficiently, which you can, then everything is great. So I don't know why they even teach the NFA thing anymore. since the 60s. I don't know. It's like the NFA thing is a little bit more straightforward in terms of like, oh yes, I see this OR bar causes me to go either direction simultaneously, but this, yeah, this is fun, and then you get a nice little DFA at the end, and you can do pretty much arbitrary complex things. Because like I said, you can do complete inversion of entire regular expressions. You can do intersection of arbitrary regular expressions. You can do XOR of arbitrary regular expressions. Those all satisfy this rule. Of course, normal disjunction you can do, and you can do the clean star and concatenation of inversions and concatenations and intersections and all kinds of crazy stuff. So it has more power than most regular expression engines and is more efficient than most of them. The Red Grep guy did benchmarks against RE2 and found that on some cases he was better, on some cases they were better, but RE2 is like a heavily optimized long-running development project by Google to do DFA-based regular expression matching. But whereas when you compare it against, say, Perl, it's like it always wins, right? Because Perl is doing backtracking all the time. Yeah, so there's like other mathy bits. I could talk about some of them maybe, but does everybody sort of follow this? Yeah, go.
Do they have a bound on the number of characteristic derivatives in terms of the size of the regular expression in a nice syntax?
Do they have a bound in a nice syntax?
So I mean, like,
yeah, let me just look for that because there are a lot of theorems in here about that kind of thing.
because that is maybe not linear, but that could be where we move the exponential block into, we have to compute exponentially many derivatives before we're sure that
Right, for sure, and then we would be equivalently bad to the normal construction.
yeah,
Right, for sure, exactly. Now,
although perhaps on different cases. Which
right,
could be
perhaps in different cases, and
Because you exponentially blow up when you compile it, and then you can run it linearly from then on.
well, that would be a big difference. Is that the NFA construction, the exponential blow up is in space, whereas here, even if there was one, it would be in time. So that's actually a potential trade-off that you're making. I'm not saying this is exponential, but even if it were, that would be an interesting fact. The other thing is that, what was I going to say about that? No, I forget.
Okay.
Okay, I'm going to look for what they say.
Conceivably, the concatenation step, if you take a derivative of a concatenation, it doubles the length of your regular expression. So you could have an exponential blow up in space also. Something like that if you have to do n derivatives and get 2 to the n. A 2 to the n sized expression at the end of that. With no simplifications. Just based on what you've shown here, not actually thinking about
Yeah.
it seriously.
So, every regular expression R has a finite number dr of types of derivatives, types being similar derivatives. At least one derivative of each type must be found among the derivatives with respect to sequences of length not exceeding dr minus 1. So that's the base number that they give us, which is to say that we won't have to match in more cases. We won't have to search deeper than the number that there are, which is what gives us this boundary level. That's not really answering your question. That's what's letting us say that we can stop here. This theorem, right? It lets us say we can stop because we know we won't find more because that must be dr minus 1, right? Well, because dr minus 1 actually is here because there's 2 of them, right? But then we have to do this to make sure that we actually, in fact, hit it. So you actually do that much work, but that's fine. Yeah. So this is the proof of this, blah, blah, blah. They have all this stuff about unique sets of equations that we don't actually use for the part that I'm interested in, so I didn't read it as carefully. But the last characteristic can be found in terms of the previous derivatives. So I'm not sure. I did look for that when I, like, not specifically, but I did look, a little bit for runtime stuff when I was reading it. And I don't know if I didn't at the time find anything that was as satisfying as I would have liked on them having even considered that. And by them, I mean this one person in this one paper. There are a lot of papers written about this paper, and written about other things about this paper. So someone has definitely considered that question, but it might not be in this particular piece. Yeah. Oh, this is a fun theorem. This is the sort of thing you have to do when you're in an academic paper that here we sort of assume, even though it's not necessarily true. Things like the derivative of any regular expression with respect to any sequence is a regular expression, because otherwise all of this is invalid.
It has to be well formed. Yeah.
So, yes, it is. They say so.
Yeah.
Proof by it is in the paper. Yeah. So the simple parts of the top, the appendices, I think are all proofs. So they might talk about this a bit, but yeah, the runtime, they mostly talk about it being finite in terms of like terminating.
That is helpful. Yes.
So like terminating, yes,
Plus one does terminate.
does terminate, but yeah, they also, there's this whole section of the paper I didn't even read about multiple output circuits, which can be interesting, but is not what we normally use regular expressions for. So I didn't really talk about that very much. But yeah, if you think about, because the whole thing here is that a regular expression, they don't talk about regular expressions as defined, they talk about them as defining these sets, but only in a loose way. Really what they're after is defining automata. They're using regular expressions as a shorthand for defining automata, and then there's a whole section on, so we can define multiple output automata, that's fine, right? Which it is, but not a thing we normally care a lot about. So yeah, I'm not sure so number of states is exactly equal to number of distinct derivatives, and runtime is exactly equal to number of distinct derivatives times like there's a factor there, but it's growing in a like fairly straightforward way, because you will find it's number because in number of distinct derivatives steps of lengths you will find it. So it's like a constant factor of number of derivatives. So it's order of number of derivatives time. But number of derivatives might be exponential with respect to, I don't even know, like with respect to bit size of the regular expression input. Like what are we even doing our runtime in comparison to? So it's an interesting question.
What is Unicode, for example?
Oh, yeah, so RedGrep is Unicode, and it's fun. He did it in the obvious way, which I totally agree with, but a lot of people are a little bit uncomfortable with, which is that Unicode is fake. It's still just bytes, and so he just does bytes. And then when you're like, oh, match this Unicode character, he's like, cool, that's byte this, and byte this. So like, yeah, and you just do matches. So his dot is implemented as the character classes that represent all the valid Unicode ranges in UTF-8 byte sequences, and stuff like this, but the matching engine is all in bytes, which means he has an alphabet size of 256, which is very helpful. Otherwise, this can get crazy in terms of alphabet size. So restricting alphabet size can definitely help.
Does RedGrep use this algorithm?
RedGrep does use this algorithm.
Okay,
yeah,
cool.
yeah. If you look at RedGrep and the talk on RedGrep, he also uses this algorithm, or at least a maintainership. I doubt that, but they all exist, and you can look at them, right? They work.
That's a little bit like it terminates.
Right.
Scale.
Yeah. Well, like the most recent commit on RedGrep was 4 months ago, so it is active, but that commit was to fix it to work with the newest LLVM API, so it compiles. So like, he's maintaining it in that he cares whether it still compiles or not, but not maintaining it in terms of like making lots of improvements, because he has a real job.
You mentioned that you can use these sort of constructions to build some things that are more complicated than the toolkits that like Perl regular expressions often give you.
Yeah. The specific things that people in a lot of the posts I read talk about that they found very exciting are not, and and, which is intersection. Neither of those operations are particularly common in classical regular expressions. You can sort of get in Perl using negative look ahead.
Yeah.
You can't get full not, but you can cheat using negative look ahead. However, it's implemented in the least efficient way possible, and negative look ahead is the #1 cause of exponential runtimes in Perl regular expressions.
Yeah.
So you can get full negation and you can get intersection, basically for no additional cost, which is a lot of people actually talk about this not in terms of being a better way to do regular expressions, but in terms of a way to add functionality without adding cost.
Right.
I'm interested in it partly from that angle and partly from the angle of just like this seems like a nice clean way to build these to me, which is nice.
About 30 years ago, I wrote came up with a really elegant way to match C comments using ampersand. I can't remember it anymore, but I remember getting really pleased with myself at the time. Some of these extra operations that you don't have in regular expressions.
Right. Yeah, for sure.
So my question continued to, does this algorithm extend to some of the things that people do that are not regular, like back references and stuff? Or are those strictly outside even these?
Right.
Because they are still, this is actually a regular language and back references are not regular.
So what I would say is that if you can, so these rules do not encompass anything that is not like standard Boolean logic operation plus these couple things. But if you can think of a way to write a rule for the derivative satisfying this of any operation you want to add, then once you have that definition written, this will apply.
Right.
But there is a proof that I can remember that you can't actually match, like when you start using back references and so forth, you can define sets that aren't regular and can't be matched by a DFA because DFAs have limitations on what they can.
For sure,
Right.
For sure, it is very possible that you can invent syntax that you can't write a derivative for that matches this rule. But if you can, any operation for which you can match this rule, the rest of the algorithm will apply to, because this algorithm is generic and doesn't actually depend on the rules at all. It depends on this definition.
Right.
These rules are for convenience of implementation.
So it's more likely then that if back references do have that property, that there is no formula that for back references. that
Certain
uses
uses of back references.
Sure. Yeah.
Recursion definitely.
Right.
Actually, the thing that I would use regular expressions most often for is, for basic parsing. So if I have a regular expression, I put in some brackets and then, you get a specific, like a sub-expression or a regular expression that matched in. You know what I'm talking about there?
Right.
So like, you get out the match and then you get the specific, sub-matches that you want to match on. So is this powerful enough to handle that type of situation?
Yes, of course.
What depends on what kind of matching you're talking about.
Like just putting brackets.
He's just talking about capture groups.
Yeah. Oh, capture groups. Okay, that's what they call it.
Yes. Yeah. If you're talking about capture groups, then yes. If you're talking about paren matching, then that's definitely something that regular expressions don't do.
No, obviously.
But yeah, capture groups.
Capture groups are trivial here. That's how it plays out in the first place. You just have some of your transitions labeled as remember that you took this transition in some piece of memory, and then when you get to an accepting state, you omit not only yes I accept, but you omit all of the things that you kept track of as you went along the path, and those are your capture results.
Okay.
Cool.
Yeah, that's how you implement capture groups on a DFA. That's not really related to the derivatives. You can do that on any DFA.
Sure. So long as you build the DFA in such a way that you remember that you should.
Right, you definitely have to mark your transitions, and you have to have some storage somewhere to put that in, and there are implementation considerations, but from a theoretical standpoint, there's nothing.
And that particular implementation you're talking about, that person that handled that particular case, that particular use situation.
Oh, I would assume so. I don't know. I didn't see whether Redcross did that or not. But RE2 definitely does. Like if you're just that's what I would say. Like if what you're interested in is, I want to use a faster regular expression library in my actual code, you should definitely just use RE2 because it's industrial strength and well maintained and fast. And it's what Google uses for every regular expression internally. So you know it's going to be maintained until RedRep is industrially stable and they just deprecate RE2, which may have already happened, but it hadn't happened yesterday. So, but you can never be sure with Google. But yeah, if you're just looking from an engineering standpoint for something, then RE2 is good. If you want to build a regular expression engine, then you should definitely use this.
We're a bit over. If we take a break so people can escape.
Yeah, for sure.